Hey everyone, welcome. Grab your notes and get settled in because today we are mastering the absolute core foundation of all electrical theory. Seriously, whether you're out there troubleshooting a massive industrial power system or you're just trying to wire up a simple little LED on your workbench without it bursting into flames, it all comes back to the concepts we're going to cover in this explainer. We are breaking down Ohm's law from top to bottom, and by the time we wrap up today, you're going to have complete, absolute control over how electricity behaves in your circuits.
Okay, let's kick things off with a pretty wild piece of scientific history. So Ohm's law was developed by a German physicist named George Ohm. Now, back in his day, they obviously didn't have the fancy digital multimeters that we take for granted today. So to actually develop his theories, Ohm undertook these crazy experiments where he measured electrical current by literally touching live circuits with his bare hands. Yeah, just to see how much it hurt. And as you might imagine, he very quickly learned that the higher the current, the more painful the shock. I think we can all agree we are incredibly lucky that we can just do the math today, instead of using our own personal pain tolerance as a voltage meter.
So what actually is Ohm's law? Simply put, it's just the mathematical relationship between voltage, current, and resistance. It defines exactly how these three foundational forces relate to and influence each other inside any electrical circuit. It's like a perfectly balanced scale. If you change just one of those elements, Ohm's law tells you exactly how the other two are going to react.
Here's our roadmap for today's explainer. We've got 1. Introduction to Ohm's law. 2. The Ohm's triangle method. 3. Voltage and current relationships. 4. Resistance and current relationships. 5. Protecting components with resistors. And finally, 6. The final circuit test.
Moving right into Section 2, the Ohm's triangle method. Now, strictly speaking, there are 3 different algebraic formulas you'd need to use for Ohm's law, but honestly, you really don't need to memorize them. We have this amazing mental cheat code that makes navigating the math incredibly simple. To use this cheat code, you just need to know your 3 main variables. V stands for voltage, R stands for resistance, and I stands for current. Now, I know what you're probably thinking. Why is current represented by an I? Why not a C for current or an A for amps? Well, the unit of current is the ampere, which was named after the French physicist André Ampère. A couple hundred years ago, when he was doing his pioneering experiments, he referred to the varying amount of electrical current as intensity. So when his work was published, the letter I was used, and, well, it just kind of stuck forever. You might also sometimes see the letter E used instead of V to stand for electromotive force. But to keep things easy for our purposes today, just stick with V, I, and R.
Okay, so here is how you build this mental cheat code. Step 1, just draw a simple triangle. Step 2, write the letter V at the very peak, and put I and R at the bottom, drawing lines to separate them all into 3 little sections. And step 3 is how you actually use the thing. You just simply cover up the letter of the specific variable you are trying to find.
This brilliantly illustrates the exact math you need to do. It's so cool. Let's say you have a circuit and you need to find the voltage. Just imagine covering up the V with your thumb. What are you left with? You've got I and R sitting right there side by side. That means you multiply them together. Voltage equals current times resistance. Want to find current? Cover up the I. Now you're left with V over R, stacked exactly like a fraction. So current equals voltage divided by resistance. Need to find resistance? Cover the R, and you get V divided by I. It is practically foolproof.
All right, Section 3, voltage and current relationships. Now that we have our formula totally locked in, let's analyze how these forces interact using some real data. Imagine we have a basic circuit hooked up to a 3-ohm resistor. If we apply 6 volts from a battery, we'll measure a current of exactly 2 amps. Now, look what happens if we double that voltage, say by hooking up 2 6-volt batteries in series to give us 12 volts total. The current completely doubles alongside it, jumping right to 4 amps. Double the voltage again to 24 volts, the current jumps to 8 amps. So the absolutely crucial takeaway here is that current is directly proportional to voltage. Think of voltage as the pushing force. It is exactly like the pressure from a water pump. If you swap in a bigger pump and apply more pressure, more water flows. In our circuit, if you apply more voltage, more electrons are pushed right through the wire.
And when we say electrons are flowing, we aren't talking about some slow, tiny little trickle. Just look at this absolutely massive number. If you have a standard 1.5-volt battery powering a 1.5-ohm lamp, your triangle tells you that V over R, 1.5 divided by 1.5, equals exactly 1 amp of current.
But physically, what actually is 1 amp? It is exactly 6,242,000,000,000 free electrons passing from that battery through that lamp every single second. It's mind-blowing. And as long as the battery can maintain that electrical pressure, that massive river of electrons keeps the lamp shining at full brightness.
Moving to Section 4, Resistance and Current Relationships.
So we know what pushing the electrons does, right? But let's see what happens when we start actively pushing back. Let's look at another data set, but this time we're going to keep our voltage locked in steady at 6 volts. If we start with a 3 ohm lamp, we get our baseline current of 2 amps. But what if we double the resistance to 6 ohms by placing another identical lamp into the circuit? Watch what happens to the current. It drops exactly in half, down to 1 amp. Double the resistance again to 12 ohms, and the current halves again to just 0.5 amps. If you built this in real life, you would actually see those lamps becoming noticeably dimmer and dimmer. This perfectly proves that current is inversely proportional to resistance. Double the resistance, you get half the current. Cut the resistance in half, you double the current.
To really visualize this, think about the atoms inside a standard copper wire. They have these free electrons in their outer shell that naturally just bounce around in random, totally useless directions. Our voltage comes in and organizes them, pushing them all uniformly in one direction so they can do useful work. Resistance is the ultimate opposition to that flow. It's like a bottleneck. It is actively trying to prevent those 6 quintillion electrons per second from getting through the wire.
Section 5. Protecting components with resistors.
Now, stopping electrical flow might sound like a bad thing on the surface, but it's actually what saves your electronics. This is where the abstract math of our triangle saves you actual money and keeps your components from literally melting. If you take a standard, highly sensitive little LED light and connect it directly to a 9-volt battery, you've got a major problem on your hands. The battery has way too much pressure, pushing far too much current through the LED's tiny internal wiring. The result? The LED instantly blows out. Total destruction. But if you calculate the exact amount of opposition you need and physically solder a resistor into that same circuit, you intentionally choke the current down to a completely safe level. The LED is projected and it shines perfectly.
This quote right here perfectly summarizes the absolute control you now have. We can increase the current by increasing the voltage or reducing the resistance. We can reduce the current by increasing the resistance. It's beautiful in its simplicity. You are now the master of the electrons. You dictate exactly how much flow happens by manipulating these simple, predictable levers.
And finally, Section 6, the final circuit test.
All right, students, let's put this newfound power to the test with 2 real-world problems. Here is problem number 1. You have a lamp with a measured resistance of 240 ohms. You plug this lamp right into a standard wall outlet in the US, which provides 120 volts. What will the current be? Visualize your Ohm's triangle. We need to find current, which is I. Cover up the I in your mind. What are you left with? V over R, right? Voltage divided by resistance. That's 120 divided by 240, which gives us exactly 0.5 amps. See? If you followed that logic, you perfectly understand Ohm's law. You nailed it.
Now for problem number 2. And fair warning, I am not going to just hand you the answer to this one. Let's say you take that exact same 240 ohm lamp and you take it on a trip across the pond to the UK. You plug it into a UK wall outlet and your trusty multimeter tells you that you are now drawing a current of 0.958 amps. Using your triangle cheat code, what is the applied voltage of a UK wall outlet? Think really carefully about which letter you need to cover up and what exact math that leaves you with. Crunch those numbers and see if you can solve the true voltage of a UK power grid all on your own. Keep experimenting, keep testing your circuit safely, and I'll catch you guys in our next explainer.